But let's go on to the globe because that's what we're going to be talking about for the most part. The outside of the eyeball is created by the sclera, and this is a type 1 collagen layer, very thick, very tough. Well, actually, it's not that thick. Everything's relative because the eye is only about 24 millimeters long, which is about an inch. But the sclera is pretty tough. The front of the eye is formed by the cornea, and this is the clear area. Now, the interesting thing here is that the sclera and the cornea are both made by the same type of collagen. And the reason the cornea is clear is because, one, it's organized a little bit better as far as how the collagen is arranged, but more importantly, the cornea is relatively dehydrated compared to the sclera. And I'm going to go into that a little bit more in a couple of slides. In the back of the eye, the sclera forms the optic sheath going back to the brain. Now, the cornea has 5 layers you need to know about. On the surface is the epithelium. This is several cell layers thick, and this is constantly regrowing, and people have abrasions and things like that. Very painful, but it heals very quickly. Underneath the epithelium is a Bowman's layer, and then a stroma, and the stroma is the main body of the cornea. It's formed by that collagen, and if you have a perforation into the stroma, you can actually get scarring. As we go down, we have Descemet's membrane, which is actually a basement membrane to the endothelium. Now, the endothelial layer is probably the most important layer in the cornea because it's only 1 cell layer thick, and that's how I've drawn it here. And these cells, they don't duplicate. If you kill off these cells, the other ones just get bigger to take up its place. And so you're born with a certain number of endothelial cells, and they decrease over time. This layer is very important because it constantly pumps water out of the stroma back into the eye, and it keeps the cornea relatively dehydrated. Now, if you have a problem with that layer, then you're going to get some swelling of the cornea. I'm going to show you that in a second. What this picture shows is a slit lamp photograph of the cornea. This patient has some dendritic ulcers here, which are a little out of focus and probably very difficult for you to see. But what I did want to show you is that when you shoot a slit of light into the eye, you can actually get a sense of how deep in the cornea things are. Now, this is the front of the cornea, this is the stroma, and this is the back of the cornea. And when we look at a lesion like this, it's mostly on the front, mostly in the epithelial layer. Let's take a better look here. This is shooting a light beam the other way. Here's the front of the cornea, here's the stroma, and this is probably the back of the cornea here. And of course, this is the iris underneath. But you can see here a big circle, which appears to be in the deepest layer. This is just a little shock wave in the endothelial layer from an object bouncing off the front of the eyeball. But what I wanted to show you here is just that you can use your slit beam to actually visualize each layer of the cornea. And you can also use it to gauge how thick the cornea is. Now, this is a patient with a corneal ulcer, and you can see here that this slit beam going through this thing gets very thin here, and that's because the cornea, the stroma, has thinned out quite a bit and is actually on the verge of perforating. In fact, this cornea is so thin here that right in the middle of this ulcer it got clear, and it's not clear because it's healthy, it's clear because it's so thin it's about to perforate. Now, if you have a break in your endothelial layer, which happens sometimes with certain ectatic disorders, or even with trauma, or if you have, let's say, very high pressure inside the eye, then you can have water actually push into the corneal stroma, and when that happens, the eye will turn white. And so this cornea is no longer clear, it's white, just like the sclera out here. Now, when I first started studying the eye, for some reason I thought there were 2 chambers in the eye. There's the back and the front, but there's actually 3 chambers. There's the vitreous chamber in the back, a posterior chamber sort of in the middle. This is between the lens and the back of the iris, and then there's an anterior chamber in the front. Now, the vitreous chamber in the back, the posterior chamber, is filled with vitreous humor, which is a jelly-like fluid, and when you're born it has the consistency of jello. It kind of wobbles, it's firm, but as you age you get little pockets of liquefaction where it kind of liquefies, and over time you can get so much that it kind of pulls off the back of the retina, and this is what we call a posterior vitreous detachment. Very common, almost always harmless, but it's one of those things that can create floaters, and people complain of seeing stuff floating around. It's usually stuff on the back surface of this vitreous. Now, this is a video showing what that looks like in real life. I'm going to decode it before I start it, though. This is the front of the eye, so this is the upper eyelid. This is the surface of the cornea, and this is the lower eyelid. This is the anterior chamber, just a space of fluid, and here's the front of the lens, and this is the back of the lens right here. And if you look behind the lens, what's back there? Well, that's the vitreous jelly, and there's some stuff here. So let's go ahead and play it. And you can see that behind the lens there's like almost like a sheet. And what that is the vitreous is kind of collapsed forward, and what you're seeing is the back sheet. So behind that is a bunch of liquefaction, and in front of that is the actual vitreous itself. Very common to see this on exam. Let's go ahead and take a look at the rest of the eye. There is, of course, the iris. That's the colored part of the eye. The ciliary body, which is a muscular area, which is actually contiguous with the iris. And the ciliary body does a couple things. One thing it does is it pulls on the lens via these little zonules. And these zonules attach to the lens to the ciliary body in a 360-degree trampoline type arrangement. And when the ciliary body contracts, it actually is a sphincter muscle, so it comes this way, and the lens zonules relax, and the lens gets rounder, and that's how you see close up. The lens itself, you can actually think of it kind of like a peanut M&M. There's a hard candy shell on the outside, the capsule. Then there's a chocolate layer, or the cortex, and then there's a peanut in the middle, and that's the nucleus. Now when we do cataract surgery, what we do is we tear a hole in the candy shell in the front, then we run a tool in here that acts kind of like a jackhammer and breaks up the nucleus and the cortex, and then we suck all that out with a vacuum cleaner, and then we inject a new implant inside of the capsule where it sits right here in the appropriate position. So let's take a look at a patient with a very mature cataract just to see some of this anatomy. Now this patient's cataract has gotten so bad that the chocolate layer has liquefied and become kind of white and milky. The nut has hardened and turned kind of brown and sunk to the bottom of the milk, and the hard candy shell, the capsule on the outside, is still intact. We know it's intact because otherwise this whole eye would be filled with white stuff, but it's not. It's all self-contained right there. Now the zonules are real important for keeping the lens in the proper position. This patient had a trauma, and his lens dislocated. All the zonules out to the side here ripped, and the lens has fallen backwards somewhat. And you see the stuff floating here? It kind of looks like jelly or jello kind of floating there. Well, that's vitreous from behind the lens, which is kind of protruded and come around in front of the lens into the front part of the eye, and that's never a good thing. Moving back into the eye, this is a photograph.